Yeah, good morning, everyone. In today's class, we just discuss about what is actually thermistor. So, thermistor is a simple type of resistor, or we just say that it is a thermally sensitive resistor, which is used to measure the temperature changes. As the temperature is changing, how the resistance of that particular component will change. So, we just say that thermistor is a thermally sensitive resistor. So the thermistors they can be measure can measure the temperature uh, about the range of across the range of -40 to 150 degrees Celsius, right? So the different operations of what you can say classifications, particularly we just deal with the uh, how this thermistor look like generally. So the thermistors can take any shape, that is either it may be in the rod shape. You can just see this diagram. So it is in the rod shape or disc shape or bead, right? So this is the semantic way of just seeing the thermistor, how the thermistors can be manufactured in different shapes. So see, we just started with the thermally sensitive resistors, uh, is nothing but a thermistor, and who is having the range of -40 degrees Celsius to 150 plus degrees Celsius, right? And these are the different shapes of the thermistor, how it look like. So now thermistors have been actually classified into two different varieties or categories. We say that is negative temperature coefficient and positive temperature coefficient. So, what is actually this negative temperature coefficient thermistors? So, first of all, we just discuss this negative temperature coefficient thermistor. So, as the what you can say resistance of these NTC thermistors decreases proportionally with there will be an increase in the temperature. So this is actually this particular phenomena says that the negative temperature coefficient thermistors are in which the resistance and temperatures are reciprocal to each other, and we say that particular behavior come under the category of negative temperature coefficient. So what is positive temperature coefficient thermistors? So in this particular thermistors, we just say that the resistance and temperature relationship is directly proportional. It means that as we increase the temperature, the resistance also increases, and as we decrease the temperature, the resistance also decreases. Now, this particular aspect is very important to understand the various types of the thermistors. So here, how these thermistors can be manufactured. So actually, how these thermistors have been, what you can say, the manufacturing part of thermistors can be easily known as that we just start with the negative temperature coefficient thermistors. They are commonly made up of oxides of the metals, and these metals may be manganese, cobalt, and nickel, and also copper. So and so on, right? So here we need to understand that the negative temperature coefficient thermistors are commonly made up of oxides of the metals. So manganese oxide, cobalt oxide, nickel oxide, and copper oxide, and so on. So what about the positive temperature coefficient? So when we see the positive temperature coefficient thermistors, they are generally made by introducing a small quantities of the semiconducting materials, right, into a polycrystalline ceramic. So you can just see this, the negative temperature coefficient actually are crystallized from semiconducting materials such as silicon and germanium. When it comes to the positive temperature coefficient, so it is actually come under the category of polycrystalline ceramic. So there's a basic difference between the classification of the thermistors. Either it may be negative temperature coefficient or positive temperature coefficient. Right. So we just started with the definition of thermistor and how this thermistor look like, and then we have gone for the different categories of the thermistor. What is the basic principle on which the thermistor is working? So the basic principle on which the thermistor is working is the change in the temperature will be directly related to the change in the resistance, and definitely when we talk about negative temperature coefficient, and these relationships will be reciprocal to each other, and this can be converted into electrical energy. So now that is the reason basic phenomena by which we can say that this is nothing but they are also known as transducers. So what is actually the meaning of transducers? Transducer will convert one form of energy. The components which are which will convert one form of energy to the another form. We just say that particular phenomena as the uh, transducer. So this will come under the category of transducer. So here, what is a basic principle? See, just now we have studied about the positive temperature coefficient. So what is the basic principle on which the positive temperature coefficient thermistor is working? So we had a very clear idea in the last slide that there is the relationship between the resistance and the temperature is directly proportional. Therefore, we just say that when we talk about positive temperature coefficient, so we just say that the resistance of these type of thermistors increases with the rise in temperature. Now, this is an important aspect. You can just see this schematic diagram where how this resistance is changing with respect to the temperature. Now, we just move on to the negative temperature coefficient working principle. You can just see that in the schematic diagram, when temperature is taken on the x-axis and the resistance of the component will be taken on the y-axis, you can just see there are three different materials which are similar to, you can say that to thermistor is a resistance temperature detector, thermocouple, and also thermistor. So here, when we talk about the negative temperature coefficient, the resistance of the negative temperature coefficient decreases with respect to the increase in the temperature. I already told you that the negative temperature coefficient is nothing but in which the resistance and temperature relationship will be reciprocal to each other. Now this aspect is very important to understand the applications. In the later section we just discussed this, how this negative temperature coefficient character uh, makes this thermistor very specific important component in the industry, not only in the industry but also in the household equipments, right? We'll just see it after a few minutes. Right now, what are the applications, right, of this thermistor? Since when you talk, see, in general, right, first of all we'll just go for in general applications of the thermistor, then we'll just understand the applications of the negative temperature coefficient. So here the thermistor is a versatile component and which is used for various applications, numerous applications where the temperature is a factor which is to be considered. Definitely when I talk, we just talk about thermistor, then definitely I'm talking about the relationship between the resistance and the temperature will come into existence. Now, depending upon the type of application specific, we can just say either it may be positive temperature coefficient or negative temperature coefficient. The depending upon the type of application, we'll use PTC or NTC. The application part is actually classified into positive temperature coefficient thermistor and the negative temperature coefficient thermistor. Here we just concise ourselves to the applications of the negative temperature coefficient. When we just see this applications of the negative temperature coefficient, we can particularly we just we take the aspect of medical application. So here in the medical application, medical purpose, the thermistors are used to determine, if we just say that is called fever thermometers, fluid temperature, and in dialysis equipment also we just use this thermistor, and we talk about negative temperature coefficient thermistors are used in the fever thermometers, fluid temperatures, and dialysis equipment. And we're actually in the household will use this thermistor. So in the burglar alarm, refrigeration and air conditioning, uh, fire reduction, and also to control the temperature of the oven will use the uh, negative temperature coefficient. Now, I think that you got a very clear idea regarding what is actually the meaning of thermistor, what is how this thermistor is looking like, what is the basic principle on which the thermistor is working, and what are the different categories of the thermistor, and what are the different applications of the negative temperature coefficient are, right? With this, we can just say that just a minute. Right. The when we talk about the important different applications of the thermistor, you can see the application of the thermistor not only in the uh, few whatever the few applications we had learned in medical purpose and also in the household equipment. There also the negative temperature coefficient thermistors are used in the automotive applications, and also for food handling and processing industry, especially for storing the food and the food preparation. Maintaining the correct temperature uh, is very critical to prevent the food borne illness. Right now, this is very important aspect, right? So like this, you will have various application of thermistors, and this negative temperature coefficient thermistors can also be utilized to control the temperature of an incubator, right? You can understand what is incubator is all about. So for this particular incubators also, you just take the help of the negative temperature coefficient thermistors, right? So with this, we can say this the semantic relationship, right, of the negative temperature coefficient and also the positive temperature coefficient, right? So with this, we can just have a very clear, we got a clear idea about the thermistor, right? We just move on to the semiconducting topic, because just now we studied that the negative temperature coefficient of thermistor is also having the same property as the semiconducting material. So for that particular aspect, in this particular class, we need to understand only the semiconductor, and particularly intrinsic semiconductor. Why? Because in the PTC, that is positive temperature coefficient thermistor, we just use this polycrystalline semiconducting polycrystalline materials, right? So in the unit one also, you just discuss about single crystal and polycrystal crystalline material. So here we need to understand what is actually the meaning of semiconductor. Semiconductor is nothing but it is the component in which the electrical resistivity of the component lies between conductor and insulator. We just say that particular definition as the semiconductor. And when I say intrinsic semiconductor, definitely I'm talking about a pure semiconductor. And when you talk about the extrinsic semiconductor, you already had an information that is purely, it's not exactly pure. Pure semiconductors are intrinsic, and the impure semiconductors that will come under the category of extrinsic semiconductor. So that also the important classification of the semiconductor. You already aware that the conductor is having the charge carriers, right? Charge carrier of the conductor is only electron, but in the case of semiconductor, where the charge carriers are not only the electrons but also holes. With in the later section, we'll just discuss about this particular aspect very clearly, right? So now, for this particular topic, you need to understand what is the semiconductor. When we just define the semiconductor with respect to the bands, what we studied at the last class, that is origin of energy bands in the solid. So we know that how this conduction band and valence band is formed, and what is actually EF. EF is the Fermi level below which all the electrons are completely filled. We just say that this particular EF is nothing but Fermi level, right? So with this, the conduction band, the difference between the conduction band and the valence band is nothing but we say that forbidden gap or forbidden energy band gap. We just discuss this particular aspect right, later in this section. Now we need to understand what is actually the meaning of Hall effect in today's class. A very important definition in the process of phenomena by which the we nowadays also we just use the different applications of the Hall effect. So Hall effect is nothing but when a metal or a semiconductor is placed in a transverse magnetic field, right, which is carrying current. So the voltage is generated, and that voltage which has been generated is known as Hall voltage, and the phenomena is said to be Hall effect. And this particular Hall effect has been discovered by Edwin Hall in the year 1879. Right. So the Hall coefficient is actually, what is the meaning of? See, when I say Hall effect, so what is a Hall effect phenomena, and what is Hall voltage? Just now you just discussed. You can just see the schematic diagram also in order to understand very clearly. So the Hall coefficient is also, you see, R suffix H is nothing but Hall coefficient, which is equal to the ratio of the induced electric field to the current density with respect to the magnetic field. Right, you can just say that this is RH is equal to EY by JX into B, where we can say that JX is nothing but the current density. Whenever when you talk about the current, when it is entering the electrons, as they are entering into the solid material, right, or metal or semiconducting material specimen, so definitely they will acquire the character of that particular material. So now we just call that particular material the current which is passing through the metal or semiconductor, it will acquire its characteristic. And we now say that it is not only current, but you just say that it is a current density. You can just see this formula in which RH is equal to E suffix Y by JX into B. There is a derivation related to this, and we can just see it when we have the nodes. So RH is equal to EY by JX into B, where E suffix Y says that the electrical current is in the Y direction, and B say that the magnetic field is going in the X direction, which has been is seen by means of the JX. Right. With this, we can see that the this is about the Hall effect and Hall coefficient. There is a applicable. What is applicable? What are the different applications of this Hall effect? Okay, just now we just discussed what is Hall effect, what is Hall voltage, and what is the Hall coefficient, right? So, what are the applications of Hall effect? Very clearly, so the current carrying charges, the sign of the current carrying charges can be determined. Either it is a, when you talk about a semiconductor, so if I want to know that the given semiconductor is a p-type semiconductor, n-type semiconductor, that is by using this Hall effect, we can just know that is it a p-type or n-type semiconductor. This is called the sign of the current carrying charges, which can be determined, right? So the carrier concentration can be measured. So just now we had the concept of carrier concentration. So what is actually the meaning of carrier concentration? So carrier concentration in us is nothing but the number of charge carriers per unit volume of the given element, the number of charge carriers per unit volume. So when I say the number of charge carriers per unit volume, so number of charge carriers, when you talk about semiconductor, the charge carriers are not only the electrons but also holes, right? So therefore, we just say that carrier concentration of these electrons and holes can also be determined. So when I say carrier concentration, the flow of charge carriers. So the mobility of this charge carrier can also be measured, and very important. The power flow in the electromagnetic waves can also be determined with the help of the Hall effect. We can see when we just there is a separate chapter regarding the electromagnetic waves. So that particular topic we'll just discuss when we go to the next what you can say unit. So the total power flow in the electromagnetic waves can be determined with the help of the Hall effect, right? So now with this is topic of Hall effect and its applications, right, we need to understand the different aspects and different applications of this intrinsic the negative temperature coefficient resistance. So we move to the semiconductor, intrinsic semiconductor. When you just see this intrinsic semiconductor, you can the left hand side we are finding out that there is a formula which is given by P, and all there is a formula N which is given by N. So when I say, so you can just see what is actually capital T is the absolute temperature, and P is the hole concentration in the valence band, and N is the electron concentration in the conduction band. And here you can just see capital NC and capital NV are the effective density of states in the conduction band and in the valence band. So now this is about the basic definition of how this semiconductor is related to, and particularly we just talk about intrinsic semiconductor. Now, so with this particular information, we just say that we just move actually to next topic, the next class, where we will find that there are different various numerous applications of the what you can say the semiconducting devices. So for that instant, we need to understand some basic parameters, not only the simple definition, but also we need to explore the idea of the given topic, and by which we can understand the important aspects of that particular component, right? So when we just started with this chapter, unit 2, chapter 1, so some of you may get or you may not get the exact understanding of this particular topic, since this topic is what you can say, it's a topic where you need to have a very good imagination, and also that imagination is put with the perfect blend of mathematical calculations, by which it has been proved that the semiconducting charges are nothing but not only the electrons, and you'll find that the electrons and holes are the two types of charge carriers, right? So now by this, what you can see that we just start our video. So how we are going to, we just start the video of the thermistor and also the Hall effect. We just see the now the video, um, a very short video by which we can understand more clearly about the thermistor and also the application of the Hall effect, right? And so we just start with this. First of all, we just go for the Hall effect thermistor first, and then we just start with the Hall effect, and then we'll understand the thermistor also, right? So
Hello, Dan Nelksky here from howtomechatronics.com. In this video, we will learn what is Hall effect and how Hall effect sensors work. The Hall effect is the most common method of measuring magnetic field, and the Hall effect sensors are very popular and have many contemporary applications. For example, they can be found in vehicles as wheel speed sensors, as well as crankshaft or camshaft position sensors. Also, they are often used as switches, MEMS compasses, proximity sensors, and so on. Now we will go through some of these sensors and see how they work, but first let's explain what is the Hall effect. Here's the experiment that explains the Hall effect. If we have a thin conductive plate as illustrated and we set current to flow through it, the charge carriers would flow in a straight line from one to the other side of the plate. Now, if we bring some magnetic field near the plate, we would disturb the straight flow of the charge carriers due to a force called Lorentz force. In such a case, the electrons would deflect to one side of the plate and the positive poles to the other side of the plate. This means if we put a meter now between these two sides, we will get some voltage which can be measured. So, the effect of getting a measurable voltage, as we explained above, is called the Hall effect, after Edwin Hall, who discovered it in 1879. The basic Hall element of the Hall effect magnetic sensors mostly provides very small voltage of only few microvolts per Gauss, so therefore these devices are usually manufactured with built-in high-gain amplifiers. There are two types of Hall effect sensors, one providing analog and the other digital output. The analog sensor is composed of a voltage regulator, a Hall element and an amplifier. From the circuit schematic, we can see that the output of the sensor is analog and proportional to the Hall element output or the magnetic field strength. These type of sensors are suitable and used for measuring proximity because of their continuous linear output. On the other hand, the digital output sensor provides just two output states, either on or off. These type of sensors have an additional element, as illustrated in the circuit schematic. That's the Schmitt Trigger, which provides hysteresis or two different threshold levels, so the output is either high or low. For more details how the Schmitt Trigger works, you can check my particular tutorial for that. An example of this type of sensor is the Hall effect switch. They are often used as limit switches, for example in 3D printers and CNC machines, as well as for detection and positioning in industrial automation systems. Another contemporary applications of the Hall effect sensors are measuring wheel speed or RPM, as well as determining position of crankshaft or camshaft in engine systems. These sensors are composed of a Hall element and a permanent magnet, which are placed near a tooth disc attached on the rotating shaft. The gap between the sensor and the teeth of the disc is very small, so each time a tooth passes near the sensor, it changes the surrounding magnetic field, which will cause the output of the sensor to go either high or low. So, the output of the sensor is a square wave signal, which can be easily used for calculating the RPM of the rotating shaft. Thanks for watching, and for more tutorials visit my official website howtomechatronics.com.
Called a thermistor. I originally needed it for measuring the water temperature in a set of experiments, determining if cold water boils faster than hot. But just for fun, I also got it to turn on this PC fan when the heat was too high. What's a thermistor? A thermistor is usually a ceramic or polymer material with two wires connected to it. The key is that the thermistor's resistance changes with temperature. With some, the resistance increases as the temperature increases. Those are called positive temperature coefficient, or PTC thermistors. With others, the resistance decreases as the temperature increases. Those are called negative temperature coefficient, or NTC thermistors. I couldn't find a thermistor locally, but some quick research turned up that automobile coolant temperature sensors are just thermistors in a protective case, which was a good thing since that saved me having to make a case of my own. With this one, there's only one obvious place to connect to, this threaded part. So where do the two thermistor wires go inside? Well, one goes to the threaded part and the other goes to the brass case. So I wrapped one wire tightly around the case, and after attaching a ring terminal to a wire and finding suitable nuts, I attached another wire to the threaded part. I then connected up a meter and put it on the resistance scale. Remember, the resistance changes with the temperature. I put my fingers on the probe part and it started to heat up. Sure enough, the resistance on the meter started to decrease as the temperature increased. So it contains an NTC, or a negative temperature coefficient thermistor. To be useful, I needed to know what resistance matches what temperature. Unfortunately, I couldn't find a resistance to temperature table for this particular one, so I had to make my own. To do that, I prepared a tall container, this soda can with all the paint sanded off. I filled it with water and put the probe part of the sensor in the water. I also put in my kitchen thermometer. The long length of my thermometer is why I went with a tall container. For my purposes, I needed to know the resistance to temperature values for temperatures near the freezing point of water. So I put the whole thing in my freezer until the thermometer read near 0 Celsius, or 32 Fahrenheit. Then I took it out, connected my meter to measure resistance, and put it on my stove heating element. I then started recording the resistance on the meter and the corresponding temperature on the thermometer as the stove element heated up the water. I stopped once it reached boiling, which is 100 Celsius or 212 Fahrenheit. And here's the chart drawn using the data from my table. As you can see, the resistance decreases as the temperature increases. You can also see that it's a curve. The whole reason I'd gone through this process was to do some experiments to determine if cold water boiled faster than hot water, as some people think it does, and to find out why that myth might exist. That resulted in this graph of water temperature as it was heated up over time. But that's a whole other topic, which I cover in another video I'll point out later. Here's the fun I had making a PC fan turn on when the thermistor gets too hot. First, here's the circuit without the thermistor. It's very simple. The positive from my homemade power supply goes to the positive of the fan, and the negative of the fan goes back to the power supply. When I turn on the power supply, the fan starts spinning. Now here it is with the thermistor. The positive from the power supply goes to one end of the thermistor. The other end of the thermistor goes to the positive of the PC fan, and the negative of the PC fan goes back to the power supply. But this time when I turn on the power supply, the fan doesn't start spinning. That's because the thermistor is nice and cool at room temperature, and so it has a high resistance. The fan needs a certain amount of electrical current going through it in order to spin. But the higher the resistance in the thermistor, the lower the current is going through the fan, and the resistance of the thermistor is high enough to make that current too low. Now I use this hair dryer to heat up the thermistor. That causes the thermistor's resistance to decrease. As it decreases, the current increases. And when the current's high enough, the fan starts spinning. Notice that the fan is blowing on the thermistor, making it cool off more quickly. Here I'm showing the airflow direction using this tissue paper. As the thermistor cools, its resistance increases, and that causes the current going through the fan to decrease. After a minute or so, the current is too low to keep the fan spinning, so it stops. Well, thanks for watching. See my YouTube channel, rimstar.org, for more videos like this. That includes the video containing the experiments to test if cold water boils faster than hot water, and why people might think that. Another on how to power a compact fluorescent light using just 2 AA batteries. And one on how to make a solar panel out of transistors, in this case to power a calculator. And don't
Now, students, with this, I think that you got a very clear idea regarding what is actually the usage of thermistor, and also the Hall effect applications, where actually the Hall effect has been used for various application. We just know whatever the video I have shown you, that is the sensor, Hall effect sensor. So like this, we are having various applications of the Hall effect. So these particular videos are meant, right? You will get different types of videos in the YouTube, but right, this is meant for your in order to make your understanding more comfortable, such that you can understand with the lecture. You can you can understand the topic which has been taught in the class more easily with this with ease. You can just understand it. So that is the I'm trying to do that, right? So thank you everyone. Thank you for your patience. With this, we just end our today's class. Again, in the tomorrow's class, we'll meet again. Thank you everyone.